Hi, good evening all. Welcome to the Week 6 live interactive session of Operating System Fundamentals. My name is Ranjita. I'm a PhD scholar at Department of CSC, IIT Hyderabad. So in the previous class, we'll quickly go through the topics covered in the previous class, and then we'll look at the questions from the previous year as well. Well, I'll just share the slides, and then we can quickly go through them. Yeah, so in the previous class, we just got started with process scheduling, and we looked at first come first serve scheduling. In between, can somebody confirm कि I'm audible? Probably you can unmute yourself and speak, or you can put it in the chat. Thank you for confirming. So we'll just take, and so in the previous class, we were looking at first come first serve. Majorly, we looked at first come first serve scheduling algorithm. So in this class, we'll get started with shortest job first. So we did see what it is. So in shortest job first algorithm, based on the CPU burst time, the processes will be scheduled in the order of like whichever process is having the minimum CPU burst, that process will be scheduled first. So in this example, if you see here, process P1 arrive at time 0, P2 arrives at time 2, P3 arrives at time 4, and P4 arrives at time 5. And the burst time of P1 is 6, burst time of P2 is 8, 7 and 3. So when the shortest job for scheduling at time 0, if we see that only one process is available. So at time 0, P1 is available. So P1 should be executed first. I'm not sure why P4 is being executed. I think it's assumed that all the arrival time of all the processes are 0. So then the smallest process available is P4. Oh, sorry. Yeah, P4. So P4 is scheduled first. Then after that, the burst time of P1 is the smallest, which is 6. So then P1 is scheduled. Then P3 is scheduled after that, which is having 7. And then P2 is scheduled, which is having 8. I don't think they have considered arrival time here. So I'll just draw and show you. Yeah. So, if we take this example of P1, P2, P1, P1, P1 is 6, P2 is 8, P3 is 7, and P4 is 3. So, in shortest job first, the one with the smallest burst will be executed first. So, we can first arrange them in the increasing order of the time. So, it will be P4 followed by P1, then P3, and then P2. That is 3 less than 6 less than 7 less than 8. So this is the order in which the process will be executed. Now let's draw the Gantt chart and see how much is the average waiting time. So we are assuming all of them are starting at 0. So uh, P4 will be executed for 3 time units. After that, P1 will get, it will execute for 6 time unit. So P1 is waiting for 3. Then after that, P3 will be executed for 7 time units, followed by P2 for 8 time units. So 9 plus 7, 16. So the average wait time here is 0 plus 3 plus 9 plus 16 by 4. So which is 7 actually. So that this is how, and this is an example of a shortest job for scheduling. So when we are given with the CPU burst, just arrange them, and this is possible when all of them arrives at the same time. So arrange them in the decreasing order of their CPU, I mean increasing order of their CPU burst time, and then we can schedule in that order for shortest job first algorithm. So here, though we say CPU burst, it's actually the next CPU burst that is based on which we will be scheduling, right? So in general, it is not possible, or it's very difficult to actually predict the upcoming CPU burst. What will be the CPU burst of process P1 or process P2 coming up? So that is normally difficult, but it is normally we predict it using the old values, like we observe the history of that particular process. Like for P1, this is how this was how the burst pattern was for the past n interval. The burst pattern will be observed, and based on that observed pattern, we do an exponential averaging using the formula tau n plus 1 equal to alpha into P of n plus 1 minus alpha into tau of n. So tau n plus 1 is the predicted next burst. This is the previous prediction. This is the previous actual value, and this is the predicted next one. So using this formula, we try to predict the burst size, and then based on the predicted value, we try to schedule the process. So this alpha, based on the value of alpha, the weightage that we give to the observed, previously observed value and the previously predicted value actually varies. So if we keep the value of alpha equal to 1, then tau n plus 1 will be equal to Tn. That is what is the observed previous CPU burst, the same we are predicting. But if the alpha value equal to 0, then the we are the previous predicted value is same as the next predicted value. So we keep this kind of smoothens the value actually. And if when we keep the alpha value alpha equal to zero point 0.5 or 1/2, then both this previously observed burst value and the previously predicted burst value, this both of them get equal weightages. Okay. So based on this predicted value, the scheduling can be done. That is about determining the CPU burst, upcoming CPU burst. So since we are using this exponential averaging, there is this every time a new value comes, the based on the value of alpha, the predictions also goes closer to the previously observed value. So at later time, as the CPU burst becomes kind of uniform, the predicted value also kind of falls in line with the observed burst value. Okay, the another thing, this was SJF. Another one scheduling algorithm is shortest remaining time first. So in this is a, preemptive version of shortest job first. So in the shortest job first, what happens is if in the ready queue we have P1, P2, P3, Pn. What we do is we see which one have the smallest burst, and then we scheduled. We just arrange them in the increasing order of the burst, and then we schedule in that order. Okay. At a later point, if a process with a smaller burst size come also, we will not be preempting it. So SJF is a non-preemptive version. But shortest remaining time first is this is a preemptive version. So this scheduling algorithm is a preemptive version. So let's see an example. It will become more clear with that. So we have process P1, P2, P3 and P4, and in the arrival time, screen is visible, right? Yeah, so 1 second. So arrival time, P1 is arriving at time 0, P2 is arriving at time 1, P3 at 2, and P4 at 3. And the burst time is for P1, it is 8, for P2 it is 4, P3 it is 9, and P4 it is 5. So initially, we if you see the queue in the ready queue at time 0, we don't have any process other than P1. So if we keep a timeline like this, 0, 1, 2, 3, 4, 5, when is it? Yeah. So at 0, P1 comes. Then at time 1, P2 comes. So at time 1, we have P1 and P2 in the queue. At time 3, at time 2, we have all three of them, P1, P2 and P3 is there. And P4 is coming at P1, P2, P3, P4. So this is what we mean when we say arrival time. Okay. So at time 0 in the ready queue, only P1 is there. At time 1, P1 is already there. P2 also came. So this is how it will be. Okay. Now when we start scheduling, we are starting at 0 itself. So 0, we have only P1 available, right? So we schedule P1. So in the Gantt chart, we will give, this is the Gantt chart. So we allot P1. Okay. P1 is allotted. This is 0. Now if you see, P1 have 8 time units. Okay. Now at time 1, P2 came. Okay. But P1 is executing. P1 have executed for 1 time unit. So now the remaining time for at time 1, at t equal to 1, we have P1 with remaining time 7 units because 1 unit is already executed. And we have P2 with time unit 4. P2 came with time unit 4. Now we will compare the remaining time of P1 say 7 and time of P2 is 4. So 4 is less than 7, right? So we will schedule P2. So this P1 will be preempted or moved out of the queue and then P2 will be given. This is the logic of shortest remaining time job first. So whenever a new process comes, we will see the current process. Is its remaining time less than the new process burst time? That is, when P2 came at time 1, we will see what is the remaining time of the current process. Current process is P1. Its total time was 8. 8 minus 1 equal to 7. 7 is greater than 4. So this will be P1 will be preempted. So P1 will be preempted and P2 will be given the CPU. Okay. Now when P2 is executing at time 3, who came? P3 came. Okay. Now at time 2, P equal to 2. So we have P1 with 7. P2 is now 4 minus 1 because 1 unit after 1 unit P3 came, right? At time equal to 2. So P2 is now left with 3 remaining time for execution. And the one that came is P3. P3 came with 9 as its burst time. So here if you see the remaining time of P2, 3 is still less than 9 only. So P2 will continue executing. P2 will continue. Okay. Now at T equal to 3. Now what happens is at T equal to 3, again a new process is coming. Okay. So at this point, we have now all of them available. So P1 is available. P1 needs 7 more units now to complete. P2 was 3 plus 1 more time unit it have executed. So 3 minus 2, which is 3 minus 1, which is 2. P2 is left with 2 more units. P3 have 9 and P4 have 5. So if you see, P2 is the currently executing process. So it is having 2 as the remaining time. Now P4 is the one who newly came. 2 is less than 5 only. So P2 will continue execution and then it will go to completion. So P2 will execute all 4 time units. Okay. Then now P2 is done. Now, what are the other processes available here? So we now it is P1 is there with 7 units, P3 is there with 9, and P4 is there with 5. So 5 is less than 7, which is less than 9, right? So now we will we will schedule P4. P4 will be scheduled. After that, P4 will run for 5 time units. After that, P1 will be scheduled again, which will run for 7 units, and then P3 will be scheduled, which will run for 9 units. So is this clear? Any doubt here? If you have any doubts, you can type in or let unmute and talk, okay? This is little tricky, the shortest remaining job first. So we just have to carefully evaluate at every arrival time. We will check whether the one executing the remaining time of that process is less than the newly arrived process. Okay. Now here again, while computing the waiting time also, we have to be slightly careful. So let's see how it is done. So let's just do this. So this was executed for 1. This is 1. 4 plus 1, 5. 5 plus 5, 10. 10 plus 7, 17. 17 plus 9 is 26. Okay. So now let's take the waiting time of P1. How much is the waiting time of P1? Waiting time of P1. So P1 got CPU when once here and once here, right? At this point, it got the CPU, and here also it got the CPU, right? Hmm. So the time it waited is 10 minus, this was P1's execution itself, right? So so this cannot be considered as waiting time for P1. So the total time when P1 got CPU minus this its execution time. So it is 10 minus 1 is the waiting time for P1. Now for waiting time for P2, P2 is starting execution at time unit 1. And if you see the arrival time, P2 came at arrival time 1. So P2's waiting time is 0. As it came, immediately as P2 came, we preempted P1 and gave it the CPU. So it is 0. Now waiting time for P4. P4 is, this is when at time unit 5, P4 got the CPU. Okay, now let's see what time it came. What time it came? It came at, P4 came at time unit 3. So it had to wait only for 2 units of time. Okay. Now P1 we already did. Now P3. P3 got a CPU at time unit 17. P3 equal to at time unit 17, it got the CPU. Now let's see what time P3 came. P3 came at 2. Okay. This is the arrival time of P2, P3, sorry. So what was that? Sorry. Time unit 2, it came 17 minus 2, which is 15. Okay. So the total waiting time will be, average waiting time for this scheduling will be 10 minus 1, 9 plus 2 plus 15, right? So it is 26 by 4, which is 6.5 units. Okay, so this is how we compute the waiting time. Okay, in general, also, if it is a normal shortest job first, also, if the arrival times are given, then we have to consider that also while computing the waiting time. Okay, in the previous class or previous week, we had assumed that the arrival time of all the processes are 0. Okay, so that's why we were just adding up these values, the time at which they were getting the CPU and averaging it. But if they are not, if all of them are not arriving at the same time, if a process is coming late and immediately after that, if it gets a CPU, then its waiting time is much lesser. So we have to check the time at which it gets the CPU and the arrival time. We have to subtract that. And in case if it was previously executed, it was preempted in between. So that time also needs to be subtracted while computing the waiting time. Just be a little careful here while computing the average waiting time. So this is about shortest remaining time first. Okay. Then the next one is the next scheduling algorithm that we will discuss is the round robin algorithm. Okay, round robin. Okay, in this case, what happens is here the CPU we will split the whole this thing to time quantum of a fixed size unit like some q units and Q units and process will be allotted to this during this time unit in a round robin fashion. So suppose we have P1, P2, P3, P4, P5, P6. Okay. So first we will start, whoever came first, we will start with P1. P1 will be first given Q quota. Okay, so first P1 will execute for Q time units or whatever be the time unit. Then after that time unit expire, it will be preempted out and then P2 will execute for the same period of time, QQ. Then when P2's time quota ends, P3 will be given the, it's like P2 will be preempted after Q units and then P3 will be given the CPU for Q units. After that, P3 will be preempted and then P4 will be given. Then P3, P4 will be preempted, P5 will be given, P5 will be preempted, and then P6 will be given. Now, after P6 is preempted, again, we will go back to, after P6 is given, we will go back to P1. So this is why it's called a round robin. So this process is P1, P2, P3, P4, P5, P6. So it just goes in a round fashion. The CPU, in a first come first serve basis, we just allocate the CPU one by one. Okay, in between, if suppose we did one round of allocation of the CPU, okay, for Q time units. Now in between, if P3 wanted only Q time units, so in this first occurrence itself, P3 will complete its execution. So in the next round, P1 will be given, P2 will be given. After that, P4 will be given, and then P5 will be given, followed by P6 will be given. Now, if in the second iteration, if P2 completes its execution in the second iteration, then after P6, P1 will be given, then P2 have completed, P4 will be given, P5 will be given, P6 will be given, and this will continue. So this is what round robin scheduling is. So processes will be given the CPU for a fixed amount of time, and when that time quota ends or expires, CPU will be preempted from the process and it will be given to the next process. So this scheduling is normally used for interactive processes, and in general, in round robin scheduling, the waiting time, average waiting time will be higher actually for the process, whereas the response time will be smaller, because say this round robin is in general used for mostly interactive processes, wherein it's a combination of short CPU burst and IO burst. So then the response time will be faster. Okay. And one another thing is, if I'm having, see now, if you see here, um, if I have 6 processes here, uh, okay, P6 got the CPU after waiting for how many times Q? N minus 1 into Q. So this will be the maximum waiting time before the process gets the CPU for the first time. Okay. So if in the ready queue, if I am having suppose n processes, then n minus 1 into this q is the time quanta. This will be the time, the max time that a process will have to wait before it gets the CPU. So this way we can have some amount of, we can do some prediction like around when the particular process will get the CPU and all that. So in general, as I said here, this round robin happens in a first come first serve basis only. Okay, that is in the ready queue, in this order, it just keep scheduling the process, but it's a preemptive. So round robin is a preemptive scheduler. It's preemptive. Okay. Then yeah, when the value of q becomes very large, its behavior kind of becomes similar with first in first out. Okay. So this value, if the value of q is very small, then it is not that good, because every time this is a preemptive scheduling, right? So when P1 was moved out and P2 is moved in, there is a context switch happening, right? So every time we preempt, at every time quantum, there is a context switch, right? So and we know that context switch do take some time. If the time taken for context switching is m, and if the time quota that we are giving q, it is less than m, then this scheduler will, the performance of the system will be very bad. So it has q always has to be the greater than m, so that the process do get some time to execute. Okay. These are a couple of points with respect round robin scheduling. Let's see an example. For example, yeah, this is the process P1, P2, and P3, and burst time is 24 and 3 and 3. Okay, so we are assuming quantum of Q is equal to 4. So let's start the Gantt chart. So at time, so initially P1 will be allotted 4 time units. Then P2 will be allotted 4 time units, but P2 needs only 3, right? So it will complete in 3 units itself. After that, P3 will be allotted 4 units, but P3 again takes only 3. So it will also complete in 3 units. Then again P1 will be allotted 3 units, 4 units. Again P1 4 units, P1 4 units, P1 4 units, 1, 2, 3, 4, 5. Yeah, P1. By this, P1 will end the execution. So now let's see the time. So here 4, 4 plus 3, 7, 7 plus 3, 10, 10 plus 4, 14, 14 plus 4, 16, sorry, 18, 22, 26, and 30. So this will be the, so now let's see the, if we see the average waiting time. So, yeah. So P1 gets a CPU once here and once here, right? P1 gets a CPU once here and once here. So that it is 10. So the amount of time P1 has to wait will be 10. And here 4 units P1 had executed. So 10 minus 4, which is 6. Amount of time P2 had to wait is 4. P3 had to wait is 7. Sorry. This is P3. Okay. 7. So average waiting time will be 6 plus 4 plus 7 by 3. Okay. So this is how we compute the average waiting time for round robin scheduling. And this is how the Gantt chart is prepared for round robin scheduling. Okay. Yeah. So now another kind of scheduling algorithm is priority scheduling. Priority scheduling. So what all we learned till now? We learned first in, first out. We learned shortest job first, shortest remaining time first, round robin, and this is priority. Of this is non-preemptive. This is non-preemptive. This is preemptive. This is preemptive. Okay. So yeah. Now, in case of priority scheduling, here what happens is different processes will be allotted some priority. Okay, priority, and based on the priority, the schedule process will be scheduled. Okay, so we arrange the process P1, P2, Pn in the decreasing order of priority. One with highest priority. So P1 will have the highest priority. This will be the highest. This will be the lowest. And the ones with highest priority will be scheduled first. And the one with lowest will be scheduled last. Okay. Priority scheduling can be preemptive as well as non-preemptive, like shortest job first. So SRTF is the preemptive version of SJF. Okay, like that, priority schedule can scheduling also can be preemptive and non-preemptive. So in case of non-preemptive, we will just in the decreasing order of the priority, as and when the processes are there in the ready queue, they will be scheduled. So at any given point of time, before scheduling a process, we will check the ready queue. and whichever is having the highest priority, that process will be scheduled. Okay, then either that process have to go for some IO, or it has to run to completion. Then release when then that process releases the CPU, the next process will be taken from the ready queue, which has the highest priority. So that is the non-preemptive version. In the preemptive version, what will happen is, even if for example we had P1, P2 like priority, in priority, as the number is smaller, priority will be higher. Okay, so probably it had priority 5 and it had 7. Okay, and now P1 is executing, and in between it executed for 3 time units, and at another process P3 came with priority 1. So P1 will be preempted out and P3 will be given. So that is the preemptive version. Okay, so this both were at 0, and at time 3, if this time unit 3, if P3 comes, so it will be like how we saw in SRTF, as and when a new process comes, we will check currently executing process is having higher priority, or the newly arrived process is having higher priority. If the newly arrived process have a higher priority, preempt the existing one and schedule the new. Okay, that is the preemptive version of it. So one of the problem with this priority scheduling is what is known as starvation. Okay, so for example, if new processes keep on coming with high priorities, all are with high priority. Then, for example, we had 7 processes. P7 we had, and P7 had a very low priority. Whereas then after that, processes keep on coming, which is having a higher priority than P7. Then it can happen that the low priority jobs will remain in the ready queue. Okay, that is starvation. Starvation means low priority job will starve for CPU. They will not get only, they will be just starving to get the CPU, but they will not get, because high priority jobs keep coming and they will keep consuming the CPU. The jobs starve for CPU. Okay, so that is what is starvation means. One solution for starvation is aging. Okay, so what aging is that, as the more you sit in the ready queue, priority will increase. As you sit longer, as you sit longer in the ready queue, priority increase. So at some point, what will happen is, even though a lot of high priority jobs comes, every time, probably at every interval of time, or as time progresses, the priority gets, for example, if P7's priority was some 50, okay, every time, every T time, the priority, like it is decremented by 1. Then it becomes 49 minus 1. Then it becomes 48 minus 1. That is P7's priority. Okay. Then at some point, P7 will have a priority of 1. So after this, even if n different processes come, Px, Py, all Pz comes with priority equal to 1, this will also get the chance, because its priority is now 1, right? So that is what aging implies. If it is priority 1 or 2 or 3, whatever, this will at some point becomes the high priority job. That is what the aging implies. So with by aging, we can ensure that a low priority job which have been there in the ready queue for a long time, it will also get the CPU at some point in time. It will not just continues to sit there. It will not starve, but instead its priority will slowly increase as it ages. And then at some point, its priority becomes the highest, and then it will get the CPU. That is the concept of aging. Yeah, now let's see an example of priority scheduling. So in case if you have any doubt, you can put it in the chat, and you can stop me as well. You can unmute and speak up as well. Oh, somebody asked to re-explain which concept was that. I missed the chat, sorry. Which scheduling? I was explaining. I think I was explaining some scheduling examples only, right? Yeah, I can go back and do that once again. SJF, right? Not shortest job remaining first. Okay. So, okay, I'll quickly explain SJF, then we'll move to the priority scheduling. First, can we take SJF after we complete the priority scheduling example? Yeah, I'll just quickly complete the priority scheduling example and can hand back. Yeah. Yes, in the priority scheduling example, again we have process, we have burst time, and we have priority. I hope my writing is clear. P1, P2, P3, P4, and P5. The burst time for burst time here is 10. 1, 2, 1, and 5. Priorities 3, 1, 4, 5, and 2. Okay. So, yeah. So, let's arrange them the priority, the tricky part of priority number is smaller the number, larger the priority. Okay. So smaller the priority value we have here, higher the priority. Okay. So let's arrange it in the decreasing order of priority. Okay. Which implies that increasing order of this number. Okay. So here P1 has the highest priority. P2 has the second priority. Okay, there's no need to mention its same number. Okay, so let's arrange them in the decreasing order of priority. So P2 has the highest priority, followed by P5, then P1, then P3, and P4. So this is the order of priority. Now we can, let's draw the Gantt chart. So the process will be scheduled in this order. So first P2 will be scheduled. P2 will execute. It is a non-preemptive version. So P2 will execute. For it takes one time unit. P2 will complete. P2 is done. Then who is the next one? Is P5. P5 will be scheduled. P5 will take 5 units of time. Okay. Then who is the next one? P1. Okay. Then P1 will be scheduled. P1 is taking how many units of time? It is taking 10 units of time. After P1, P3 will be scheduled. P3 is taking 2 units of time. And last P4 will be scheduled. P4 takes 1 unit time. Okay, so 1, 5 plus 1, 6, 6 plus 10, 16, 18, and 19. Okay, so now let's see the average waiting time here. So P2 waits for 0, P5 waits for 1 time unit, P1 waits for 6, P3 waits for 16 time units, and P4 waits for 18 time units. And divided by how many we have? 1, 2, 3, 4, 5. Divided by 5 gives the average waiting time. 6 plus 1, 7. 31 by 5, which is 8.2. Okay. So this is how non-preemptive priority schedule example is there. Okay. There is one more example. Okay. What if here, if you see that all the priorities were different. Okay. What if the two processes have the same priority? Then how are they scheduled? Okay. So in that scenario, some systems will combine the priority scheduling with round robin scheduling. So what will happen is um, if two processes have the same priority, then they will be scheduled in a round robin preemptive manner. Those two processes alone. Okay, so we will just take an exam, take such an example also, which was covered in the lecture. So again, there is process, burst time. So if you have any doubts, you can unmute and ask actually. I'm not seeing the chat frequently because I'm sharing the screen. So in case if you have any doubts, you can unmute yourself and ask as well. So P1, P2, P3, P4, and P5. So this burst time is 4, 5, 8, 7, 3. Priority is 3, 2, 2, 1, 3. So now again, let's arrange it in the decreasing order of priority. So P4 has the highest priority. P4 followed by P2 and P3. P2 and P3. Then P5 and P1. P1 and P5. 3. Okay, 1, 2, 3. So this is the order of priority. So now we'll have the Gantt chart here. So between P2 and P3, round robin will be done, and between P1 and P5 also round robin will be done with a time quanta of 2 units. Let's see such an example. So first P4 will be executed. P4 will be executed for 7 time units. Then after that, P2 will be executed for 2 time units. Then P3 will be executed for 2 time units. P2, now again P2 have 5, right? So 2 is done. Again P2 will be executed. Now again P3 will be executed. P3 will be executed. 2, 2. Now P2 is done with 2 plus 2, 4. So 1 time unit is pending. So P2 will be executed for 1 time unit. Now P3 will be executed. P3 is done with 2 plus 2 plus 2, 6. P2 is already completed. So again P3 will be executed. So P3 is also done now. 1, 2, 3, 4. 2 plus 2 plus 2 plus 2, 4. Now we have P1 and P5. Now let's see, P1 will be executed for 2 time units. P5 will be executed for 2 time units. Again, P1 will be executed for 2 time units, and P5 will be executed for 1 time unit because it has only yes, okay. So now let's okay P5. Now let's find the number 0. This is 7. 7 plus 2 9. 9 plus 2 11. 11 plus 2 13. 13 plus 2 15. 15 plus 1 16. 16 plus 2 18. 18 plus 2 20. 22. 24. 26. 27. Okay. So now how do we compute the waiting time here? What is the waiting time for P4? P4 it is straightforward, it is 0, right? Now let's take what is the waiting time for P2. Okay. So here first time P2 got it when it had to wait for 7 time units. Okay. Then P2 got it at 11. At time 11, P2 got it. But in that, 2 units was its execution time. Hmm? Then again, P2 got it at 15. Of this 15, again another 2 time units was its execution time. So from the waiting time, we have to reduce the execution time. Okay. So if we take that total in this total time, we know here 7, it has to, okay, 7 plus, we are doing for P2, right? Yeah, 7 plus, this is 11. 11 minus 7 plus 2, 11 minus 9. Plus or another we will do it this way, there will be another way as well. Now if you see in this 15, this is when it got for the last time. In this 15 we have already considered the time till here. Okay, so again it will be it was executing here, so it's again 15 minus 13. Or another way to do is for P2 is take the take this last 15. Then of that 15 minus the time when P2 got the CPU. So P2 was executed in this 50. This is the time when P2 got the last CPU. Okay. So this is 15. Now from this 15, we can subtract how of this. This is the total waiting time. Total time P2 had waited in the queue. So in that, it got the CPU here once. It got the CPU here also once, right? So it is 15 minus 4. 2 plus 2. 15 minus 4, which is 11. Is it the same? 7 plus 2 plus 2, which is 7 plus. Yeah. So this is one way of doing. This is, I think, easier way. Take the last time when that process gets the CPU. Okay. Take this last time when it is getting the CPU, that is 15. Then check in the reverse of this 15, how many times P2 was executing. So 2 unit and 2 units. So that was the execution time. You cannot add that also to the waiting time. So this 15 contains this execution time also. Okay, so we will minus it and we get the waiting time. Same way for P3 now we can do. So when was the last time P3 got it? P3 got it at 18, right? So now 18 minus, this is one execution, this is another execution, this is another execution. So 2 plus 2 plus 2, 6. Okay. So this is 18 minus 6 is 12. Now for So for P3 we are done. Now let's go to P1. P1, the last time when P1 got is 24. So of this 24, how many times P1 executed? Only once. That is 22. And P5, it is 26 minus how many times P5 executed? Yes. Yeah, so now, the SJF example we can see once again. So, yeah. So, in shortest job first, here again, what was the shortest job? The process with the shortest burst time will be scheduled first. Okay. So, what will happen is in shortest job first. Yeah. So we will arrange in the dic- shortest increasing order of burst time. And the one which has the least burst time will be scheduled first. Okay. So let's see this particular example. P1, P2, P3, and P4. And burst time of 6, 8, 7, 3. So now let's arrange it in the increasing order of the burst time. So which one has the lowest burst time? It is P4. P4 is less than, then P1, then P3, then P2. Okay, so it will be scheduled in this order: P4 followed by P1 followed by P3 followed by P2. So when we draw the Gantt chart, it will be like first P4 will be scheduled. P4 will run for 3 time units. After that, P1 will be scheduled. P1 will run for 6 time units. After that, P3 will be scheduled. P3 will run for 7 time units. And then P2 will be scheduled. P2 will run for 8 time units. Okay. So 3, it's 9, 16, and 24. Okay. Now here, if we have to compute the average waiting time, it will be for P4, it is 0. Waiting time for P4 is 0. P1 is 3. P3 is waiting time for P4, P1, P3 is 9. And waiting time for P2 is 16. So now average will be 0 plus 3 plus 9 plus 16 by 4. So it will be 28 by 4, which is equal to 7. Is this clear? Is this what you were asking for? Can we proceed further? If this is clear, we can proceed. You can type in the chat or unmute and speak up. Or is it something else that you were asking me to explain? Let's continue. So we did till priority scheduling. Okay. So the next concept that is discussed is this multi-level queue. Okay. So instead of having this ready queue as a single queue, it's also possible to have multiple queues. Actually, ready queue can be partitioned into separate queues, and we can assign use different scheduling algorithm for these different queues based on the kind of processes that we are going to schedule on them. So one of the most common way is to have two queues. One is for foreground processes, that is interactive processes, and the other is for background processes. So in general, interactive processes are CPU IO bound. Okay, there will be a lot of CPU and IO will be there, whereas these will be as compute intensive. Okay. So for interactive process, normally round robin is preferred, and for background, sometimes priority, FIFO, all that is because once you schedule it, it will run for a long time. So it's better we use such an algorithm. Whereas for interactive processes, it's their the characteristic of these processes are like they have both CPU and IO operations interleaved. So it's better we go with round robin approach. Okay. So sometimes we will, in general, yeah, this is RR and this is FIFO, and the processes will be allotted to. So the process P1, P2, Pn, it can be allotted to one of the queue based on its property. It will be permanently allotted to one of the queue, and then based on the based on which queue it is allotted, it will be scheduled. Okay. And in general, we give like 80% of the CPU time is used to schedule foreground processes, 80% for foreground, and 20% for background process. Okay, that's how this is one multi-level queue scheduling. Then another way is to have this is one way multi-level queue. Another one is to have different queue for different priority. Like we can have like for example, if we have this is for priority 1, this is for priority 2, priority 3, and priority 4. So we can define, okay, and we can have n also, however we want. So every process, so P1, P2, Px will come, it will go to either this or this or this based on the priority of the process. It will go to one of them. And within this, it will be normally round robin. Okay. So that is another multi-level queue. Another example of multi-level queue is to have in these queues in general, when the process enters a queue, it stays in that queue. It will not move across the queue. Okay, so if it gets into priority one queue, it will be there in priority one queue. It will not be moving from one queue to the other. Whereas there is another scheme called multi-level feedback queue. So in this, what happens is here there will be the processes will move across these queues. So it will be at some point it will go to so for example P1 at some point it will go to this queue, and based on some observation it can then go to this the other queue, and then later to the other queue. So the process is based on its behavioral pattern, like whether currently it is going compute intensive or whether currently it's going IO intensive. They will move it across the queues. For example, assume that we have three queues, Q1, Q2, Q3, and here all of them are round robin. Okay, this is round robin, this is round robin, and this is FCFS. FCFS. So assume that here 8 is the quantum, this is 16 is the quantum. P1 initially entered into 8 and it was executing in this queue. Okay, after a couple of its execution, what happened was it's not ending at all. Like it's getting 8 quantum, but still it's getting scheduled every other time unit, which implies that P1 is currently going for longer CPU time. So based on that feedback, it will go to RRs, the other round robin queue, which have a larger quantum. But again, if it is not getting over, it's keep on scheduling in the every other iteration, then it implies that it's currently going a CPU intensive compute intensive phase. It will give given to the FCFS queue, so that it will be scheduled, and then all its until its CPU requirement is done, until it releases by itself, it will run. So sometimes it can also happen that now, so P1 now came to FCFS. Now after some time, P1 is frequently going for context switching. It's frequently going for IO. Then it will be given to RR. But here also, if it is exiting before, it's given 16 quantum, but it is coming out in 4, like it's going for IO in 4 units of time or in 6 units of time, then it implies that it's into the IO burst phase. So, and again, it will be moved back to queue. So this is the multi-level feedback queue where processes switch from one queue to the other based on the current requirement, whether current compute intensive phase is going on or IO intensive phase is going on. Okay, so that's about scheduling. The other topic discussed in the previous session was on synchronization. Okay, so let's quickly go through the synchronization part also. So synchronization is nothing but when let's get so synchronization, like we know, we have already seen threads, right? Threads shares a lot of data segment variables, global variables. So suppose I have T1, T2, T3, and all of them are sharing some variable X. So in T1, it is getting incremented. In T2, it's getting decremented. In T3, it's getting multiplied like that. Okay. So when all of them access this global variable at different point of time, all the three threads should have a consistent view of this shared. So this is a shared variable, right? So this is a shared variable. This shared variable, all the three threads should have a consistent view of this shared variable. So to achieve that, the shared variables are properly updated, or when T1 is trying to update T2 and T3 doesn't touch it, or when T3 is trying to update, T2 and T1 doesn't touch it. So because in the middle, somebody in the middle of incrementing, if T2 goes and decrement it, then the value will be the variable will be in an inconsistent state. We will get wrong value. So to prevent that, we need what is known as synchronization. So it's a way of ensuring that when T1 is updating, only T1, T2 and T3 will not touch the variable. Only T1 will be updating. Or when T2 is updating, only T2 will touch the variable and update. That is the scenario. Now you will be thinking that how can somebody get in the middle of X plus plus and modify it? This is because normally in this is a C representation, right? This increment decrement operations are normally done in the hardware instructions, right? So what normally happens is if I have to increment a particular variable, first there will be a move operation. We will move that variable to the register. We will move it. Then we will do the add R, 1. Then what we will do? Then again we will move R2. Okay, sorry. It's a reverse. Oh, sorry. No, the value of so this way. Okay. Okay, so these are this is how the assembly instructions happen. This is for adding at T1. At T2, it will be like move. It could be some other variable or some other register. Again X. Then it will be subtract. So again R2 1. Then again X R. Now for time being, let's forget about T3. Okay. So I am at a given point of time, if X is having value 5 and T1 does an increment 5 plus plus, the value becomes 6, and T2 does a decrement. Okay. 6 minus minus, which is 5. So final value should be 5. Okay. So if that is the order of execution, the T1 has to happen first, after that T2 has to happen. Okay. Then by initial value was 5 and the final value will also be 5, right? But it can so happen that when we had just now see all these scheduling things, right? Now suppose at this point T1 was scheduled, T1 executed this, now it is moved out. And T2 is scheduled. Now T2 is scheduled. T2 is scheduled. So here T1 have incremented the value, but it have not copied it to the variable. Okay. So at this point, now if T2 comes in the variable still has the value of 5 only, right? So now here it will have value 5. It will decrement it. It will become 4 here. Now what will happen? Now assume that after this place again T1 is scheduled. So now what will T1 do? T1 will go here. T1 will update the value of X as it was 5, 5 plus 1, 6. It will make the value of X as 6. Now after this is done, again T2 is scheduled. Now T2 will go here. What was the value of R2? 4. So it will make the value it to be 4. But the actual value we should have got is 5. But because of this interleaved scheduling, it can happen that the final value that we get is 4, which is a wrong value. Which is a wrong value, right? So, so to avoid these kind of thing, we need the synchronization techniques. Now it will never see. This is an instruction, okay? Whenever there is a scheduling preemption or anything, interrupt or anything, in the middle of the instruction, it will not, the CPU will not be given to another process or anything. So if an interrupt comes also, whatever instruction it is executing, that will be completed. And after the execution of the instruction, the CPU will be given to another process. Okay, so these in the middle of this add, move, and all, nothing will go wrong. But since these are high level instruction, these are how underlying machine instructions are. So in the middle of this, if the scheduling comes, there is a possibility that we get a wrong value. So to prevent that, we need a synchronization mechanisms. Okay. So in the lecture, sir, I've discussed this with the producer consumer problem, the counter incrementing. It's all the same. Okay. Yeah. So this condition is called race condition. Okay. Based on where and how the scheduler decision is, the final value will change, right? The final value of X. Final value of X is now dependent on how the T1 and T2 instructions are scheduled, right? So we call that as the race condition. It's not consistent, irrespective. What we need is, irrespective of the scheduling, switching, whatever happening, the final value of X should be consistent always. Every execution, like whether T1 is followed by T2 or T2 is followed by T1. Okay. Irrespective of how the threads are scheduled, the value of X should be always consistent. That's what our requirement is. But in the current scenario, it is actually dependent on how the threads are getting scheduled. So we call it as race condition. Okay. Yeah. So, right. So now I will just introduce something called critical section, and will be this about the critical section. It is further explained, will be explained in detail in the upcoming week. So this particular variable that we are using, right? This X variable that is shared between these two threads. So this portion of code in thread T1 and T2 that modifies this shared variable is called a critical section. It's critical, right? Because this is shared. So we call it as critical section, and this the operation in this critical section has to be protected, or it has to happen in a mutually exclusive manner. Okay. So portion of code that modify shared variables is the critical section. Okay. So in the thread T1, this portion of code that is doing this one is forms the critical section. Okay. So the problem, critical section problem is that so So what we need to achieve here is that in this critical section problem, the thing is that only one of them have to execute at any given point of time. So the critical section problem here is to design a protocol that will solve this race condition. Okay. So when like n processes P1, P2, Pn, etc., are sharing a common shared variable or shared location, and they are trying to modify things in this shared location, then we need to design a protocol that will ensure that irrespective of the order in which they access, the variable will always have a consistent view across all the processes. Okay. So what this critical section, what is the solution is that, so if we have a critical section, okay, critical section here. So before entering this critical section, we will actually have a entry section which will ask for permission to enter the, there will be an entry section that will ask for permission to enter the critical section. Then once the critical section is entered, we need to release that. We got the permission. So now we need to give the permission to somebody else. to enter. So only one person will be doing this at a given point of time. There is this exit section, and then rest of the program is called the remainder section. So these are terminologies used. So just keep in mind when somebody says remainder section, it means that rest of the code where the shared variables are not accessed. So there is no issue if the threads schedule interfere and all. There is no issue at all because there are no common variable modification in this section. So there will be entry section which takes care of the permission. Then there is the critical section. Then there is the exit section, which releases the permission. Oh, sorry, exit section, exit section. Then there is this remainder section. Okay. Yeah. So in general, for a process, it will be there will be a like I wrote, there will be an entry section code that will ensure that we get the permission to enter. Entry section code will be there. Then critical section code will be there. Then exit section code will be there. You will understand what these codes are in the next class when sir discussed about semaphores, mutex locks and all that. Then there will be reminder section code. Okay. Yeah. There are a couple of things. Yeah. Now let's see there are some conditions to ensure that the critical section problem is solved. Okay. So one such condition is that mutual exclusion. Mutual exclusion, which implies that if process PI if mutual exclusion means that only one process can execute in the critical section at any given point of time. That is what mutual exclusion means. Okay. So if we ensure mutual exclusion, then we will be able to ensure a synchronization between multiple processes who are sharing this common variable. Okay. Then another aspect or another property of critical section solution to critical section problem is that like if no process is currently executing in the critical section, and there is one process who wants to enter into the critical section, then that process should be able to enter. Okay. So it cannot be, we cannot just keep waiting in the entry section. So entry section gives permission to enter to the critical section, right? So if currently there are like 5 processes that share this critical section, now on 4 of them are not in CS, okay, but one wants to enter. Then in that situation, if nobody else is executing in the critical section and if one process wants to enter, then this entry section decision, okay, this permission to enter the critical section should happen. It cannot be postponed indefinitely. So we call this term as progress. Okay. So this is another one property, and another one is bounded waiting. Bounded waiting is the next property of critical section problem solution. So bounded waiting says that if, for example, uh, the amount of time a process will have to wait before getting permission to enter the critical section should be there should be a limit for it. A bound must exist on the number of times that a process are allowed to enter are allowed to enter the critical session before another process have made its request and it's being granted. For example, again let's take this 5 process example. Okay. So P1, P2, P3, P4 and P5. Okay. Now P1 have entered, P3 requested. Now again, P3 is waiting. Now P2 have entered. Now again, if P1 enter, P1 and P2 keep entering, this P3 is keep on waiting there, right? So this cannot happen. So there is a bound on the number of times the process can enter this critical section when there is an already requested process waiting to get the grant or get the permission to enter. So this ensures that all the processes gets the turn to enter into the critical sections. Okay, so these are the properties of the critical section solutions to critical section problem. So where I think you will understand it better when we actually discuss about logs and other things and how these mutual exclusion progress and bounded waiting is ensured by the synchronization solutions. Okay. So with this, I think the discussion is done. We'll quickly go through the problems. Okay. Now. Uh, yeah. So let me share the screen very much. So yeah. Okay. Let's now go through the questions from the previous year. Okay. So, an operating system follows round robin scheduling with time quanta of 4 millisecond. So, assuming that the CPU is free now and there are 20 processes waiting in the ready queue, the maximum amount of time that a process waits before going into the CPU is. So here, so this is there is a this formula that I told, right? If there are n processes and the time quanta is q, then n minus 1 into q is the maximum amount of time that a process will have to wait before getting the CPU. Okay. So here n is 20 and q is 4. So n minus 1 will be 19. 19 into 4. What is the answer? What is the answer? What will be the answer? 19 into 4. 50 minus 4. 76. Okay, so the answer here is B. Hope it is clear. So the answer here is B. So the second question is a situation where several processes access the manipulator access the situation where several processes access and manipulate the same data concurrently and the outcome of the execution depends on the particular order in which access takes place is called data consistency, race condition, aging, and starvation. What is the answer? We just discussed here a couple of minutes back. Can somebody type in the answers? Okay, so just we saw, right, the variable x being shared across multiple threads. So the value of x is dependent on the order in which the variable is executed, right? So it's not consistent across all the different execution. This one. So so the value of x was dependent on the particular order in which the threads access that variable, right? And I told that issue is called as race condition. So the answer here is B, race condition. Okay. Data consistency means it is consistent across, irrespective of the order in which it is executed. The values, we always get the same value. That is data consistency. Aging is not related to synchronization. Aging is with priority scheduling. So if the low priority job spends in the ready queue for a long time, its priority slowly increases. So that is aging, and starvation is when is the issue and the solution is aging. So in case of priority scheduling, if the low priority, if there is always a inflow of high priority jobs, these low priority ones will never get the CPU, and they will just starve to get the CPU. So that's starvation. So here the answer is B. Now, next question is which of the following is incorrect? Starvation problem is when low priority processes might never get executed. Starvation problem is when low priority process might never get executed. Yeah, that is true. Aging is the solution to starvation problem where priority of a process is increased with time. That is also true. And then in priority scheduling, higher the value of the integer, higher is the priority of the process. It's actually the opposite. Higher the value of the integer, lower is the priority. So here, incorrect one is C. Okay. The answer is C. Now Q4, which of the following statements are true? Shortest remaining time for scheduling may cause starvation. That is actually true because we all, whenever a new process comes, we check whether its burst time is less than the currently executing one, right? And then we preempt and give it. So, like I told in the priority scenario, if there is large inflow of high priority jobs, similarly, if there is a large inflow of low CPU burst flow, I mean processes, then the process that have higher CPU burst will always will keep on waiting. So that this can actually cause starvation. Preemptive scheduling may cause starvation. Yes, that is also true. In case of shortest remaining scheduling, we saw. In case of preemptive priority scheduling, also that is possible. Round robin is better than FCFS in terms of response time. Yes, that is also true. So the answer here is D. Okay, all of them are. Which of the following is incorrect? The time quantum is extremely small. Round robin can result in a large number of context switches. That is true. If Q is very small, then it ends up in lot of context switch. So the bare minimum value of Q is that it should be greater than the context switch time. The average turnaround time of a set of processes does not necessarily improve as the time quantum size increases. Okay. The average turnaround time can be improved if most processes finish their next CPU burst in a single time quantum. Which one is incorrect? So here all A, B, C are correct. That is, average turnaround time of a set of process does not necessarily improve as we increase the time quantum size. Yeah, that is true. If even beyond a point, if we increase the turnaround time, will not improve. And the same holds with the and turnaround time. We have actually there is a graph which says that if all the if the turnaround sorry the quantum time, if the time quantum is somewhat equal to the CPU burst time of all the processes, if all the processes can complete their CPU burst in the given time quantum, then the average turnaround time actually improves. So all of them are correct. So the answer here is D. Yeah, next one. So mutual exclusion implies that if a process is executing in its critical section, then all the resources of the system must be blocked until it finishes execution. No. If a process is executing in its critical section, then other processes must be executing in their critical section. No. The process is executing in its critical section, then no other process must be executing in it. So this is what mutual exclusion means. Only one process must be executing in the critical section. No others should execute in the critical section. So the answer here is C. Then next question, which of the following is correct about atomic action? While execution of an atomic action, no other instruction is executed concurrently. Yeah, that is true. So in the example that I gave, the instructions, CPU instructions like move, add, those are atomic. Okay, nobody else will interleave in between that. Okay. So incrementing or decrementing the counter as an atomic action can solve the race condition. Yes, that is true. Because in the example that I listed as the increment and decrement was not an atomic operation, but there are processors which provide increment and decrement as atomic operation. So in that case, race condition will not happen. But in our example, we did not consider it because we have the load, store, and then we have the add operation, right? So it is not atomic. So if it is atomic, then race condition will not happen. So ability to execute actions atomically can provide solution to several synchronization problems. Yes, that is also true. So the answer here is all the above. Okay. Now, next question. Bounded waiting implies that there exists a bound on the number of times a process is allowed to enter its critical section after a process has made a request to enter its critical section and before the request is granted. When another process is in its critical section, before a process has made a request to enter its critical section, bounded wait is this one, number A. A. That is, it implies that there exists a bound on the number of times a process is allowed to enter a critical section after a process has made a request to enter. So if P1 and P2 is there, P2 have made a request, P1 is in the critical section. Now, if P1 have keep on entering without releasing, to say we need permission is needed, right? So there is a limit, like when P2 have requested, then P1 can enter only a bounded number of times before P2's request is granted. So answer is A. This is the, yeah, yeah. In design protocol of critical section problem, each process must ask permission to enter the critical section in the permission to ask this critical section is done in the entry section. It then executes in the critical section. Once it finishes executing in the, it enters the exit section. Then the process then enters the remainder section. So it is entry section, exit section followed by remainder section. So the answer here is B. Okay. So first to ask permission, there is this entry section. Then we have the critical section. Then to release or allow others to enter or release this permission, we have the exit section. Then the rest of the program, which we call the remainder section. Okay. And then the last question is, which of the following is adopted to tackle the critical section problem? If a process is in critical section, no other process is allowed to enter that critical section. That is mutual exclusion. If no process is executing in its critical section and there exists some process that wish to enter their critical section, then the selection of the process that will enter the critical section next cannot be postponed indefinitely. This is what is known by progress. So this is also there. Then a bound must exist on the number of times that other processes are allowed to enter their critical section after a process has made a request to enter its critical section and before the request is granted. So this is bounded waiting. So all three are adopted to tackle the critical section problem. So the answer here is all of the above. Okay. Yeah. So with this, we are done kind of. If anybody have any queries, questions, you may please unmute and talk, or you can put it in the chat as well. If there are no doubts, then we can close the session. Yeah. Thank you all. we'll have the same session next week, Tuesday, same time, 6 to 8 for the, I think mostly synchronization related topics will be covered in week 7. So we'll cover that in the next week session. Thank you all.
Thank you, ma'am.
Thank you.